Hi, everyone. Happy Sunday. We only have 3 lectures left. Hard to believe. All right, Amir. While people join, do you want to give just a quick preview of what students can expect for this lecture and why they probably see so many guests on the Zoom today? And then we'll do announcements when a few more people join.
Yeah, absolutely. And again, we're going to go over whatever I say again, in a little bit. But welcome to lecture number 23, everyone. Today is the second lecture of our quantum hardware series, and we're going to be talking about implementations of quantum computing. Specifically, how do you actually build a quantum computer? What is the backbone technology that is being considered today, and what are some properties of these technologies that we think could build the quantum computer of the future? So with that, we're having a few guests joining us today to talk about the technology that they've been working on as a part of either their PhD or their professional experience throughout many years. Each of these guests are an expert in their field, and we're very lucky to have them. So hopefully it should be a great lecture. And the lecture will be followed by a short or potentially long Q&A session afterwards, where you can ask questions after we present the material about different technologies, about the technologies from our lecturers today.
All right, just a few announcements before we get started with a really incredible panel of presenters. I wanted to start with Akshay and I were talking. We know a lot of students are in countries being severely impacted by COVID-19 right now. Really, we're still in the midst of a global pandemic. And if you are in a place where you or your family are being impacted by COVID, we just want you to know that our hearts are with you and we're really, really sorry. But also, if you need accommodations so you can continue in the course, so you can ensure that you pass and get your certificate, please email us. So again, it's student@qubitbyqubit.org. We totally understand, and if you need to be there for your family or for yourself right now, that takes priority. So please email us. We will be happy to provide accommodations and work with you. And yeah, our hearts just go out to folks who are in parts of the world where things are still quite difficult. Now, a few course-related announcements. So again, we're really coming up quickly on the end of the course. So we have lecture today, and then for the next 2 weeks, our last lecture is on May 9th, and we only have 2 more lab sections. So this week and then next week, no lab. That final week, we will conclude with a lecture on May 9th with, again, a pretty cool guest panel. We'll have folks from IBM, people from the Qubit by Qubit advisory board, so lots of experts and leaders in the field of quantum computing coming to speak with you all and congratulate you on such an incredible conclusion to the course. So just a few more things, and the details of these I'll post in the chat, and then we'll also post on Canvas. So please check the announcements if you're still not regularly checking those. Just so you know, you will not see homework posted tonight on Canvas. We're going to do a little bit of an unconventional assignment this week. So your assignment will be to complete a technical assessment. So you've taken this if you've been in the course for a while now, either once at the start of the course or twice if you also took it at the start of second semester. We're going to have you take the same assessment one more time. And our goal here is to measure how much you've learned over the course. So that will be a completion grade. It is not graded for accuracy, though we hope to see how much you've learned. So please do your best on that. Lab this week will be a review. So the assessment won't open until after your lab section, and then you'll have 3 days after your lab to complete that. And it's 40 minutes, it's timed. So just so you know, you won't see homework posted as usual, and it will be time bound then regularly. Again, completion grade, so don't stress about the details. It's not like a final exam. It's not intended to be that way. And then the other part of your homework that we hope you'll complete this week is just a survey about the course. So we want to know a little bit more about your thoughts about quantum, your interest in continuing to study quantum computing or pursue STEM fields moving forward. And again, this is the first time we've done this course. On area, you have to complete this survey. So again, details posted on Canvas, but please do take care of that this week. And then just the last thing before I turn it over, we posted already on Canvas, but several of our TAs have volunteered to have some kind of small group, 25 students chats this coming week and the week following. So they want a chance to get to talk with you in smaller groups. No lab content, no structure, just a chance to answer your questions, tell you a little bit more about their journey into quantum computing and their current work. So if you haven't had a chance to sign up for one of those, check out Canvas. And like we said in that announcement already, we will announce a few more of those small groups that you can sign up for this coming week. So I know it's a lot. Again, this will all be posted on Canvas, but we appreciate your cooperation and participation as we kind of take care of some of these end of course logistics. And with that, Amir, I'll turn it to you and the rest of the panelists.
Thank you so much, Rachel. So just a quick review. In the previous lecture, we talked about the conditions and the metrics that we need to meet for building a quantum computer. Namely, what systems can be used for quantum computing, what are the criteria of these systems, and this lecture, of course, we're going to talk about what they look like, and also how do we compare different quantum processors, both among different platforms or using the same technology. Now, in this lecture, we will be talking about quantum hardware implementation, specifically what are different ways to build qubits and quantum processors. So to do a quick review, the backbone for quantum computing is a qubit, which is a two-level system. Now, two-level systems are just quantum systems made out of two bases. So, one example, of course, is a qubit that we've talked about, but another example is an electron spin. So for a qubit, the bases are 0 and 1. For electron spin, the bases could be spin pointing up and spin pointing down. And that's a two-level system. So with that, let's do a quick review of the DiVincenzo criteria. So the first criteria was that we are looking for scalable two-level quantum systems. So scalable in the sense that there wouldn't be any physical barriers to having a device with as many qubits as I want. Two-level system, of course, means that, again, a quantum system that can be described using two bases. And of course, quantum system is because we want to take advantage of the quantum properties for quantum computing. And these quantum properties are superposition, quantum interference, and entanglement. Next, we want to be able to initialize these qubits to a desired initial state. For example, for a lot of the algorithms that we've talked about, the algorithm starts with all the qubits being in the 0 state. So that is what we mean by being able to initialize the state of the qubits accurately. So when we say that our algorithm starts with all the qubits being in the 0 state, they are all actually in the 0 state. Next, we want a long relevant decoherence time, meaning that we want our quantum system or quantum computer to preserve its quantum properties while we're running the circuit that we want. So we want essentially our quantum circuit to actually be quantum. The next one is a universal set of gates such that we could create any quantum program that we want using this set of tools. And finally, we want to be able to efficiently measure the outcome of our quantum circuit in our quantum computing. So that is the efficiently measurable condition of the DiVincenzo criteria. And to this end, we talked about some metrics to consider when it comes to evaluating the quality of a quantum device. Namely, for coherence properties, we talked about relaxation time, or oftentimes referred to as T1, which tells us how long it takes for our qubits to decay from the 1 state, which has a higher energy, to the 0 state, which has a lower energy, and also decoherence time, which tells us for how long can a qubit, or can our qubits maintain their quantum information, their quantum properties, before they turn into a classical probability distribution. And another end of the spectrum, of course, is the operation quality. Namely, what are the gate fidelities or error rates? So how good is in each individual gate that I apply during my sequence of quantum computing? And also another metric that was pointed out last time was the readout fidelity or error rate. So how good is my readout? If the actual quantum state or the quantum state at the end of my quantum circuit is 0, with what probability am I actually going to read a 0, get a 0 when I do the readout? Or also if the quantum state at the end of my quantum computation is a 1, with what probability am I going to end up getting a 1 after I read out the state? And of course, we had this exercise where we compared 3 different 5-qubit superconducting processors. Again, these are some of the numbers that are usually reported, and I would like to just pay some attention to. And again, this is what we will see when we talk about these different quantum platforms. Usually we will see a lot of these numbers show up over and over again. Of course, or a lot of these metrics, of course, the numbers are going to be different based on the technology, but these are some basic metrics that we use to evaluate the quality of a quantum system for quantum computing. So let's talk about, so during this lecture, we're going to talk about different quantum computing platforms. Now, what we believe is that today we're in the vacuum tube era of quantum computing. And the question that we want to answer, we want to find out in the next 10, 20, 15 years, maybe I'd say 10, 15, 20 years, is what will the quantum transistor be? And to draw some comparison, this is the picture on the left is the first digital classical computer called ENIAC, which was built in 1946. It was the size of a full room, and it had less computation power than the smartwatch that I'm wearing right now. And to draw a parallel, this is the quantum, or rather the circuitry and the cable, and of course the quantum computer that Google used for the quantum supremacy experiment with only 53 qubits. Of course, 53 qubits is quite an engineering achievement, but there's still a lot of work to be done, and that's the work that will be done again in the coming decades. So for video calling, we can use different platforms. We can use Skype, Zoom, Google Meet, or FaceTime. There are options of different platforms, as different platforms have different technology and source codes in the background. They operate differently, and they have different algorithms that they execute. Now, a similar thing can also happen for quantum computing platforms. So there are different candidate systems for building a quantum computer. Or you can think of them as different species of qubits. So the different platforms that we will be talking about today are trapped ions, superconducting circuits, photonics, and NV centers in diamond. And we're going to, of course, go in depth into how each of these technologies operate and what do they entail. But that being said, these qubit species or platforms or technologies are not the only technologies that are being pursued today. In fact, there's way more. And just to use a few as an example here, there's NMR quantum computing. You can use Majoranas or topological solids for quantum computing, or neutral atoms, or silicon spins. Now, there are more technologies and platforms out there, but we can only talk about so many. So we're going to focus on 4 today, and you'll have a chance to ask some further questions after presentations. So with that, I'm going to quickly switch my slides. And I'm going to first talk about superconducting quantum computing or superconducting qubits. Okay, I think we're all ready. Yeah, so as you might know already, my research background, my PhD work is in quantum computing using superconducting qubits. Specifically, I'm focused on quantum simulation. But let's talk about superconducting qubits. So the TLDR for superconducting qubits is that we engineer artificial atoms using superconducting material that can be used as a qubit. Now, what is a superconductor, you might ask? So as electricity moves through normal material, it experiences resistance. Now, you can think of this as, the real world analogy is if you're in a crowded room and you're trying to get from one end of the room to another, all the people between you and your desired destination are going to act to slow your movement towards a destination down. Well, at least in a semi-classical world, that's one way of looking at resistance in material. As your electron is trying to move from one end of your wire to another end of your wire, it bounces off and scatters through a bunch of defects that are in the wire. And effectively, it experiences some resistance in getting from one end to another. Now, a superconductor conducts electricity without any resistance. So the current goes right through without experiencing any resistance that normal material do. So in general, material resistance drops as temperatures get lower. One way of thinking about that is the movement that you see in all these defects becomes smaller and smaller as you slow down, as you drop the temperature, and therefore your electron has an easier way, it has an easier time moving through all these defects and all these extra people you can think of them to make it from one end of the wire to another. But now for some material, the resistance actually sharply drops to zero at a critical temperature, which is usually referred to as Tc. So for non-superconducting material, you can see that the resistance or the resistivity becomes lower and lower and lower and lower as you decrease the temperature. However, for superconductors, it initially follows the same trend. The resistance starts to become lower, but all of a sudden it drops to zero at some critical temperature. Now, this temperature is usually very low for conventional superconductors. Of course, now there are all of these high temperature superconductors, which is an active area of research. But for example, for aluminum, which is a material that we use to build these superconducting qubits, the critical temperature is 1.75 Kelvin. Now, to put that in perspective, 1.75 Kelvin is half the temperature of outer space. And 0 Kelvin is minus 273 Celsius. So it's very, very, very cold. Now, let's look at what a superconducting qubit is. How do we build it? Well, so let's build a superconducting circuit, meaning a circuit that is made out of a superconducting material with a capacitor and an inductor. Now, what is a capacitor? A capacitor is an element, I have it highlighted here, that stores electrical energy. And then the inductor stores magnetic energy. Now, if I have a circuit with a capacitor and inductor, the energy in the circuit goes back and forth between the capacitor. It gets fully stored in the capacitor and then moves, and it gets fully stored in the inductor, in the other element, and then back to the capacitor and back. And this back and forth motion, since we don't have any resistance, can in theory go on forever. Now, at the quantum level, if I only have one quantum of energy here, a very, very, and the circuit is superconducting, the energy levels for the system look like this. So I have my zero energy, my zero state, a one state, a two state, all the way up to, let's say, 3, 4, 5 or higher up. And the energy one that's required to same from 2 to 3 and all the way up. So you can think of it as the distance between all these energy levels being the same. Now, a question that I want to ask of you right now is, can we use this system as a qubit? And I will launch a poll. Please let me know, please fill the poll. I'm curious to see your answers. And for reference, this system is referred to sometimes as a quantum harmonic oscillator, but you don't need to know the name. Yeah, let's take another 10 seconds and answer the poll, and then I will continue my presentation. Okay, so the majority of you said that this system can be used as a qubit. And probably the thought process behind it is, okay, here we have a quantum system. The levels are well defined. So, let's just use 0 and 1 and call that a qubit, right? But now the problem here is that if I'm trying to drive a transition, like let's say if I want to flip my 0 to 1 or my 1 to 0, I have to essentially zap the system with some amount of energy that excites it from 0 to 1 or returns it from 1 to 0. Now, the problem with that is that if I'm in a 1 state and I zap it with that amount of energy, well, the system can either go into the 2 state or the 0 state. And that's not what I want. I want a 2-level system or something that's as close as possible to a 2-level system. But here we saw that there's a scenario where you could accidentally involve the higher levels of your quantum system, and that's a bad thing. Now, in fact, the challenge is that ideally we want a purely 2-level system, but 2-level systems are very hard to come by in nature. Now, I mean, of course, my atoms friends will tell you that there are the well-defined transitions in atoms that can be treated as a 2-level system effectively. But even if you look at an atom, there are many, many, many different energy levels. Now, and the challenge that we have here, or what we want here, is that we need a transition between 2 levels that is uniquely addressable. So the amount of energy that it takes to go from 0 to 1 is different than any other distance, like any other distances in this system. So let's replace the inductor that we have with something called a Josephson junction, which I'm showing here with this box and a cross. Now, what is a Josephson junction? Well, so if we have 2 superconductors coupled by a thin insulating barrier, that forms a Josephson junction. So you have a superconductor, an insulating barrier in between, and another superconductor. Now, normally if there's an insulator somewhere in your circuit, chances are that that blocks the flow of current or electricity from one end to another. But now in this system, current will actually tunnel through the insulator. So current will flow through the first superconductor, will tunnel through the insulator, and then will continue flowing through the second superconductor. And this is actually what the Josephson junction look like in real life when we fab it. It's a very, very small layer of sometimes oxide between 2 levels of or 2 layers of superconducting aluminum. Now, what this does is that it creates a nonlinearity such that now the distance between 0 and 1 here in this new quantum system is different than the distance between 1 and 2 and all the subsequent transitions, or the distance between subsequent levels above. And now we can actually use this as a qubit because we have a 0, a 1, and I can uniquely go from between 0 and 1 without accidentally jumping to another energy level that I don't want. So this is somewhat close to a 2-level system. And the 0, 1 is going to be our computational subspace, and that's what we're going to call a qubit. Now, so this is what these qubits look like in lab. It's actually a qubit from my lab. So again, I told you that these qubits are made out of a capacitor, which is this giant pad that you see, this giant cross. That's a capacitor pad, and the other part of the capacitor is the ground. And it also has a Josephson junction. So in this case, the Josephson junction, or the sweet loop as they're called, but don't worry about it. The Josephson junctions are here. So just to give you a perspective of the size, a massive pad is the massive X is a capacitor, and the small loop here has the Josephson junctions. And of course, we read them out by coupling them to a resonator, which allows us to read the state of our qubits using microwave, and we can drive drive the qubit using microwave pulses.
Amir, could I jump in with a few questions that are coming?
Go for it, Akshay.
Okay, so a few people are asking, the Josephson junction that you showed, it kind of looks like a capacitor. So is there any relationship there?
Yeah, so actually, the Josephson junction does have some capacitance, by the way. That's a good observation. But in a sense, it acts more like an inductor, and to show that, it actually requires some bit of math that might be a little too advanced. But trust me when I say that it actually acts as a nonlinear inductor. But you are right to think that it does have some capacitance.
And then a few people are asking, when you say there's tunneling going on, is that the same thing as the quantum tunneling we talked about?
It is exactly quantum tunneling, yeah. And there are some intricacies to it that, again, comes from the physics and the math, but the property is quantum tunneling.
Okay, and then another question is about the, if you could talk a bit more about, so you have that diagram on the left, which shows this parabola. A few people were confused what the 2 is there.
Yeah, so the 2, as I said, there are higher, like the circuit that we have is not a purely 2-level system, but you have many, many energy levels. And what we're trying to do is that we're trying to engineer a system that has a unique distance between 0 and 1. Such that we can use a 0 and 1 for quantum computing, and we don't accidentally go to the higher energy levels. So the 2 is just the second excited state, and the 3 would be the third excited state. But we want to only stay in the lowest energy state, which we call ground state, and the first excited state.
Okay, and then finally, there's a question about the Josephson junction again. Why do you exactly need that insulating barrier between the two pieces of superconductor?
Yeah, so that's a good question. So again, if you go back, in the case where we didn't have the Josephson junction, where we only had an inductor, the problem that we had was that the distance between all these energy levels was the same. So none of these distances were unique, meaning that I could access, my qubit state could easily get lost in the spectrum of all these energies. But now when I add this insulating barrier, this Josephson junction, what happens is that it changes the spacing between these levels. So now I have a unique spacing between 0 and 1, and that allows me to use the 0, 1 as a qubit that I want for quantum computing.
Thank you.
Okay. And again, we'll have an opportunity for more questions during the Q&A session. So again, just to review, so this is what a superconducting qubit looks like. We read and operate these qubits using microwave signals that reach the qubit through either resonators or drive lines. Now, these quantum chips, the superconducting processors, sit in a dilution refrigerator, which looks something like this. This is actually the Dill fridge, in short, that I use in my lab for my research. Now, inside the dilution refrigerator looks something like this. It looks like a chandelier, and based on my understanding, you've already seen a few of these. Actually, you've toured my lab. So the way that a dilution refrigerator works is that the fridge starts becoming gradually colder from top to bottom, such that at the very, very base, at the lowest level of the fridge, we typically reach temperatures of 10 millikelvin, which is roughly 500 times colder than the temperature of outer space. This is, of course, for two reasons. First, we want to make sure that our circuits, the chips that we put down there, are superconducting at that temperature. But also, we want to make sure that we don't accidentally populate, go from 0 to 1 due to the energy, the energy that's surrounded the qubit in the form of heat. So if you have your qubit sitting in a hot environment, they can actually steal some energy from the environment and go from 0 to 1. And that's what we're trying to avoid. So we want to make our qubits as cold as possible. And 10 millikelvin is a good temperature. And finally, this is the microwave equipment that we use to operate our superconducting quantum circuits. This is a full rack that belongs to a single experiment, and we use these microwave devices for our quantum operations, and also to read out the state of our qubit at the end of our computation operations. So this is what one of the quantum computing, one of the superconducting quantum processors in our lab looks like. So each of these squares is a qubit, and we have two capacitor pads, and there's a very small Josephson junction going in between that you actually can't see from this view. And this chip is only 5 millimeters in size, or at least one edge of it is 5 millimeters. So these are still very small, but you can see these qubits with your bare eyes. So the size of each qubit is roughly 200 microns or micrometers. Now, you can either connect these qubits through an extra capacitor in between. So in this case, all we're doing is that each qubit here has a finger extending to the other qubit. And those fingers form, have some capacitance in between. So they act as a capacitor, and that is all we need to connect them. And of course, you can also connect them using an inductor and the mutual inductance between these two loops, but let's not worry about that. Now, what are the coherence properties of our qubits? So the state of their superconducting qubits, the state of the art T1 in quantum processors is about 100 microseconds, and so is the state of the art T2 for quantum processors. 100 microseconds is what you can replicate many qubits of in quantum processors with 50 qubits, let's say. Now, it has been shown that individual qubit T1s and T2s can go as high as 1 millisecond, actually very recently. Now, for superconducting qubits, the average gate time is 10 to 100 nanoseconds. So, as you can see, the gate times are much, much, much shorter than qubit coherence times, something to the order of 1,000 times to 10,000 times shorter. So that being said, although our coherence times might be shorter than some other technologies, the gate times are also much shorter. So that makes things work out. And the gates, now when it comes to engineering gates for superconducting qubits, you can either engineer single qubit and 2 qubit gates using microwave pulses, as we talked about, by driving the system with some microwave. Or you can use the natural hardware interactions to let the system evolve under a specific gate, or evolve under a specific Hamiltonian that implements a specific gate. Now, using these two approaches, we've been able to engineer single qubit gates that reach 99% fidelity, and also qubit gates that reach beyond 99.7. Now, even 99.9% 2 qubit gate fidelities have been demonstrated. Now, the pros and cons, let's talk about the pros and cons of superconducting qubits. So one of the pros is that it comes on a chip. You can manufacture the chip, at let's say a plant in Western Massachusetts and bring it in Boston, and it'll work nicely. It's compatible with existing fabrication infrastructure, meaning that we could use some of the techniques and the tools that have been developed for fabricating classical processors in the past 50 years to build these quantum processors. It uses microwave technology, which again is very well developed over the course of the past 70 years, almost since the Second World War. And we have access to high quality gates and readout. Now, there are, of course, some cons, namely there's loss to substrate material, meaning that since our qubits are interacting with some, some substrate, that typically takes a toll on their coherence times and the relaxation times. And they require cooling to millikelvin temperatures to avoid accidentally exciting qubits from 0 to 1, just to the temperature present in the environment. And as it stands with the current technology that we have, we need a bigger dilution refrigerator for larger processors. So if we want to operate more qubits, we need to also make this dill fridge, the dilution refrigerator, larger and larger. And that's a challenging engineering task. Now, some breakthroughs in recent years, of course, have been the quantum supremacy result by Google, which I'm sure you've all heard about by now. One more recently, as of last month, is a demonstration of millisecond coherence time in superconducting qubits. Another one was the Hartree-Fock simulation on a quantum computer, again by Google. Now, the significance of this result is that they were able to do a large quantum chemistry simulation on a quantum computer. In fact, the largest to date. And as you might have heard, quantum chemistry is one of the first applications, or is what is perceived to be one of the first applications of quantum computers. It's a very challenging problem for classical computers, and we hope that quantum computers will be able to do a better job. And this is a key step towards achieving that with a superconducting quantum processor. And finally, another key result recently was controlling and reading out these superconducting qubits using photonic links. So now what this result means is that instead of needing these microwave lines to go all the way down, all the way from your room temperature up down to your millikelvin stage to very cold, you can use optics, and that reduces the overhead needed in terms of the size of your dill fridge for having larger and larger quantum processors. Now, the ongoing research in the field is, first of all, scaling to more qubits. Want more and more qubits, such that we can do cooler things with our quantum computer and do things that classical computers can't do. Of course, an active area of research always is achieving higher coherence times, either through new designs or improving the material that is used for building these qubits. We want to engineer better quantum gates, of course, higher fidelity gates. And this is all in order to achieve error correction and fault tolerance, such that we can have the ideal perfect quantum computer that we've assumed all the way till before last lecture. And here I have the roadmap that IBM and Google have laid out in achieving these goals. And things are looking very promising. So with that, I want to wrap up my my talk on superconducting quantum qubits, and I want to pass the torch to David, who will be talking about trapped ion quantum computing. So David, if you're on the call, could you share your screen, please?
Hi, sorry, I'm getting this set up. Cool, can you see my screen?
Yep, all good, David.
Excellent. Hi, my name is David Juan Campos. Today I'm going to talk to you about trapped ion qubits. So before, just a short bio. I was born in Peru, that's explaining my weird accent. I did an undergrad in Mexico in physics, then a PhD in physics as well in quantum computing at University of Maryland. And then worked for 2 years at QxQ, which is a quantum computing startup. And then currently kind of switched gears and moved as a postdoc in neuroscience at Harvard. So following Amir's lead, the too long didn't read part is for trapped ion qubits is that it takes Mother Nature's qubits, atoms, and engineer around them. So this is going to be the thematic of this short talk. And just to give you a quick analogy, what the systems that we have in trap ions for quantum computing is akin to, say you take the ocean, you grab some fish, put them in a fish tank, and that will be some level of control. But actually that picture is even a little bit incomplete, because actually the level of control that we have is more like getting circuits into fish and telling them where to do and exactly where to be and what to do at every single time. So that's the level of control that we are striving at this point. So we take whatever nature gives us, and then we engineer around what we have. Just to follow in the numbers from Amir, let me actually give you a laser pointer. The best detection fidelity, which is how good are we at detecting either if the qubits are at 0 or 1, it's pretty good. It's 4.9 of fidelity. The best single qubit gates fidelity, which is how much of 0 or 1 each qubit will have, is also pretty good in atomic ions. The best 2 qubit fidelity is also good, that it's getting improved over time. And the excellent coherence, which means that for how long my system remains quantum, it's been reported to be more than 10 minutes. So that's extremely long. And one of the, of course, nice things about working with the system is that it is reconfigurable. It allows you to do computation and simulation in the same system. And because of the properties that I'm going to expand in this talk, it allows you for full connectivity. So it's different than when you design your chip. In these specific cases, you get all connectivity, all-to-all connectivity. And I'm going to expand on these points as I go. So first, what is an atomic qubit? I mean, why would you care? And one of them, the things is that to build one, you need atoms, of course. And this technology has been known since the 50s. So this is kind of ancient technology to some extent. But the steps are the following. So you find an atom with 2 outer electrons. So for example, in this specific case is calcium. And then I rip apart one of the electrons, and then it becomes ionized. So this atom, instead of being just neutron in this specific case, it becomes positively charged. So this extra electron over here makes it look like a hydrogen atom. And what I meant about like humans and mankind understands these systems pretty well is because we really understand hydrogen atoms. So the fact that we are engineering a system around something that looks like a hydrogen atom helps a lot. And from there, you of course want to trap them, because if you have atoms, they could be anywhere. So you want to design some sort of cup to trap these individual atoms, so to localize them in the space. So the question here is whether you can see them and manipulate them. So I'm going to lay out the steps. So, but first, I'm going to talk about how the traps work. So I'll talk, designing a cup. And of course, if these are charged particles, they have positively charged. If you have an electric field, and this is my atomic ion, the atom will feel a force. So it's going to be pushed towards the right. Of course, you could do better. This is not a cup, of course. This will look closer to a cup. So the electric field is pushing towards all the sides. So that in this specific plane everything is inwards. But it turns out that this sort of violates nature. And this is not really what we will have in real life. What we have in real life is something that looks like this, with the electric field that is pushing the atom goes in, but everything that goes in should also go out. So this is not a cup. This looks more like a saddle. So something that looks more like a triangle. If I put something here, it's going to roll off on the side. But if I put it here, it's going to be trapped. But that's not really a cup. So how people back in the 50s realized how to fix this is by making the cup rotate. So that's a sort of a clever trick, where you have a ball and you make the saddle rotate so fast that in average, the ball or the atom or the positively charged atom will see a cup. So that's how we trap them. And this is really robust. Again, this is known since the 50s and it's being done as a part of the platform. But I'm going to highlight how interesting this is, because we are talking about individual atoms that we can trap. So this is how it actually looks. Like if you go to a lab in quantum computing that you can see, you will see, depending on the trap, you will see something that looks like this. So what we're seeing here, you see a bunch of bright spots. Each of these bright spots is a single atom. So I want to maybe a little bit and look at it a little bit longer. Because to me, even now, after working on this for so many years, it is still amazing that we as humans have the capability of trapping individual atoms. So in this specific case, the pink kind of letters is just to number them. But this is telling you one important thing of this platform, that here, for example, loading this thing is super fast, is milliseconds, or we don't really think about that when trapping them. And we trap, for example, 47 atoms, and those are 47 qubits. That's Mother Nature's qubits. And they remain trapped they could remain trapped there for days, weeks, months, and I've seen trap atoms for months even in specific conditions. So this, of course, is a little bit of gymnastics. You have a 2D distribution, and then it becomes to 1D, and the actual distribution that is used most of the time is the linear, because it's easier to control. And also, the separation really well. So this is just how we trap them. We have, traps that can do way more than this. I've seen traps for 200 qubits. And so the qubit number for us, for this specific platform, is not really necessarily a problem in that sense, because we can keep them for so long. So this is how it looks in an academic lab. But more modern implementations of this setup is through these little traps. So in these specific pictures, I'm showing how the trap looks like. And as I mentioned, it needs an electric field. If it needs an electric field, it needs electrodes. So each of these little wires give you some electric field right at this slot over here. And of course, if you zoom out, you will see a bunch of traps being trapped right in the slot. So, and this is just a zoom out, and this is how it would look like. So I would also like to highlight the fact that the way we make these traps, it's through well-known manufacturing techniques. So making a bunch of these traps is as simple as making integrated chips. So there is that. So the question now, once we know that we have many qubits and we can play with them and do these funny geometries, is, well, I want to do something interesting with them. So how do we operate? So first, we need to have vacuum chambers. So I would argue that any quantum system will require some level of isolation. By isolation, I mean isolation from space, from external stuff. So you need vacuum in this specific case because you don't want gases or air or anything to touch your fragile quantum states. Or the interactions that happen should be really fast. So I always like thinking that you need isolation in space, which is sort of cold or vacuum, or isolation in time, where the operations happen so fast that external agents don't have the time to hit or interact or mess your quantum state. For the case of trap atoms, we also use lasers to control, and I'm going to expand this in a little bit. So here is an enthusiastic practitioner trying to just align lasers, and it's really pretty, and it's always fun to work with. And also we need a bunch of control electronics to control the electrodes, to control the lasers, the vacuum, and so on. So that's almost a must. And this is how a quantum computer looks. Of course, this is from my old company, so I cannot show much, but you can see what I just explained. That is just the electronics. Inside there is a vacuum chamber and also the lasers. So to finish this part of trapping, when I mentioned that atoms, because they are charged, so like charges repel each other. So if you have two positive charges, each will feel the same. But if I have a charge here and a bunch of them in a line, and another one here, the last ion, charge ion, will feel this one, and so on. All the possible combinations will be there, and this is what I meant when I was talking about the full connectivity. So the graph for the connectivity will look like these pretty kaleidoscopic shapes. So saying that our qubits are trapped, our qubits are connected, then how do we implement single qubit gates? And by now, I believe that you guys had like a really excellent introduction of single qubit gates and how to get them rapid frequencies and Ramsey experiments and so on. But here I'm gonna give you a more in-depth way at which you will do these operations in an actual setting, in a practical setting. So let's first start with with a preparation. So again, the single qubit will tell you how much of 0 and 1 I will have for individual qubits. So how much components. And specifically for trap ions, these systems are very much like two-level systems, as Amir mentioned. Of course, there is a ball of dirt that you need to take care about, but again, we really know how they behave. So by preparation, in this specific case, I say like, well, you trap it, you have to trap them and keep them there for long. And then what we do, we shine laser light, and then we do the measurements. So what I'm trying to say here is that when you shine the laser for some amount of time, let's say tau, for this specific case, if I shine laser light for 0 seconds, I will see nothing. If I shine laser light for 50 microseconds, I will see something maybe. So imagine that I make this experiment many times for different times of the laser light. So this is what I would see. So what I would see is that for, say, if the laser light is set for 25 microseconds, it will be here. This is only one experiment per point. So one experiment per shot. But here it becomes interesting at, say, 50 microseconds for this specific case. So at 50 microseconds, what happens? That you see that it is 1 in this one shot, but it also looks like there is something noisy around here. And in quantum mechanics, noise is a really good thing because it gives you something extra to think about. So it turns out that when you repeat this experiment many times, you get an average. And that average will look like this. And probably if you remember your classes, this is what a rabbit frequency is. And what is even more interesting is that if you park here, let's say around 45 microseconds, so I prepare my atoms, I shine my laser for 45 microseconds, and then I measure, I will see that 50% of the times, I will see my atomic ion being 0 or 1. So, and of course, if I go to say 50 microseconds, I will see that that proportion of being 1 becomes higher now. It's higher now. And I will go like that, and here right at around 80 microseconds of shining my laser lights, I have the high certainty that it will be a state 1. So this is a full flip from 0 to 1. So we have good control on that, and as you can see, it's really close to the 99.99% that I mentioned before. This is just an example, but people do it way better and faster. So this, of course, this implementation, the pi time, the amount of time it takes from go to 0 to 1, it's about 75 microseconds, but the best implementations are like 5 microseconds, which is fairly short. So that's how we prepare them. That's how we get the single qubit gates, how we tune the proportion between 0 and 1 for each individual qubit. But then the question is, how do you actually perform gates? What is interesting about quantum computers is that you can do 2 qubit gates. So let's see. So if you have a line of ions, and say like these 2 ions are in spin state 0, so they are in state 0, and say that I shine 2 laser beams. So these laser beams, what I'm gonna do is that they're gonna physically push the atoms towards one direction. So that's sort of like a laser light just pushing the atoms. But it turns out that you can tune the interaction such that if you have now this, you prepare this atom in 0 and this in 1, and you shine again the laser lights, what you will see is that the atoms are now pushed, and the -1 is pushed on the opposite side, and the 0, of course, goes to the same way. So this time is about 5 to 25 microseconds for the most recently reported gates. But basically, as you're saying here, that this allows for quantum gates. And again, I would like you to stop a little bit to think about this, because I want you to ask, just as a general question, well, what happens if my atoms are in a superposition of 0 and 1? How will they behave? These examples that I point out are just for pure spin states, but what happens if they are 0 and 1? And that point is essentially how we create entanglements, because they are correlated now. So this amount of time for normal configuration is about 5 to 25 microseconds. So the pros and cons of this platform, of course, that they have excellent quantum properties. Traps are made with really known techniques. And lasers and photonic technologies are quite mature at this point in time. And the high quality gates and readouts, it's something that I feel is one of those things that make this platform so robust. One of the cons, of course, that the operations are slow. as I mentioned, my units for a single qubit at 2 qubits are about around like to the order of microseconds. But if you take into account that the amount of time for the coherence time of these systems is 10 minutes, then the ratio of amount of operations per unit of coherence time is not too bad. So this is what gives us hope that, or even this approach is even valid, that we can work with this. And as I mentioned before, this specific platform needs vacuum. But again, if you're using anything physical, you will need some way to isolate it. So in the case of photons, what happens there is that they happen so fast that, of course, the interactions and the dirt that happens doesn't really hit. So it's isolation in space and time. Part of the breakthroughs, just following what Amir told us, is that a bunch of demonstrations have been done in the past year. So this over here about the demonstrating CCD sort of chip quantum computing has been demonstrated quite recently, published in actually like just last few weeks ago. And making algorithms with these systems is one of the new have been also done, and benchmarking as well. And I should also emphasize the fact that trapped ions was probably the first one that they actually implemented a 2-qubit gate with the intention of mega quantum computing back in the 94, I think, right after the proposal of people saying, "Oh, this is interesting to do. We should do it." That happened, and of course, trapped ions also allow you to do way more complicated stuff, like simulating what happens, say, at CERN with a quantum computing. So that's another paper, and also people also have demonstrated ways to untangle different traps or different modules of these quantum devices at the distance. And what I feel is more important for the field and also for pretty much. Now, when a unicorn, a company now is valued more than $1 billion in the public market. So IonQ, the company I worked before, announced that they will be public in the near future. So they're just finishing the paperwork. So one of the, of course, ongoing research that people is kind of working a lot these days is trying to scale to more qubits. So as I mentioned, you really don't want, say, 50 qubits or 30 qubits or something. To make something interesting, it's true that you will need way more qubits. So more in the course of hundreds, or if it is possible to thousands. But of course, we are kind of far from that right now. But now I would argue that going to the course of 80, 100, it is attainable in the near future. But of course, you want to expand it to even further. Achieving error correction of fault tolerance means that, as I mentioned, if you got 99.99% and you make many qubits, let's say 100, then that becomes 99.9 to the 100, which is at this point a lower number. But it turns out that through many clever techniques, you can actually avoid this lowering in fidelity. And that's why it's known as error correction, that they try not to be dependent on the number, more on the configuration of your gates. And of course, as I mentioned, Honeywell, which is a super huge company, I think 100 billion valuation, and IonQ have now laid out all the roadmap for the next year. So yeah, the next years are going to be definitely right for everybody to jump in and try to make their best on pushing this specific technology and the other ones as well. So with that, I'm done. And thanks again.
Yeah, thank you so much, David. So before we hear from the rest of our panelists, let's take a 5-minute break, and then we'll restart at 3:05 Eastern time, by the way.
Imagine
Hi, everyone. Welcome back. So I'd like to now ask Eric to start sharing his screen. Eric will be telling us about solid state defects and how they can be used as qubits. Thanks, Eric.
Yeah, thanks, Amir. Okay, can you guys see my slides? Great. So hi, everyone. My name is Eric Burson, and today I'm going to be talking about another kind of qubit, which is formed from something called a solid state defect center. And sort of the TLDR, the abbreviation is that we take a solid material and then we add some defect into it. And these systems I want to kind of highlight they're okay for quantum computing, but they're really great for making something called the quantum internet. And I'm going to talk about that in a little bit. A little bit about me. I'm from a town you've probably never heard of in Illinois called Long Grove. And I actually originally didn't know that I was interested in physics. I started studying biomedical engineering. But sort of through that, I found out that quantum mechanics was super cool and really useful. And now I'm a graduate student at MIT in the electrical engineering department. So you guys already have a huge leg up on where I started off because I had to go from biology all the way to physics. But here I am now. So I said this term, the quantum internet. And you guys have maybe heard of this before, also described as quantum networking. And basically what this means, what people are talking about, is the idea of sending a quantum state or sending a qubit over a very long distance. So why would you want to do that? So it turns out there's some applications in something called quantum cryptography, which basically is a way of having two people, say Alice and Bob, if they have entangled bits. So Alice has some qubit and Bob has some qubit and they're entangled, they can do 100% secure secret key sharing. And this is also sometimes called quantum key distribution. So that's one interesting application of sending qubits long distances. Another is something called quantum enhanced sensing. And without getting too much into the details here, the idea is that there are a lot of sensing applications. So for example, gravitational wave measurement. You maybe have heard of the experiments at LIGO and places like that. Where they're sensing something very, very small or very, very small signal. It turns out that if you have lots of sensors that are separated by very, very far different distances, but they're entangled, that you can actually do enhanced sensing. And the last thing that's maybe most obvious to the people from this class is connecting quantum computers. You know, if you've got a computer in LA and a computer in Washington, DC, you want to have them be able to talk to each other. And you'd really like to be able to have them sending quantum states to one another to communicate. And the way we do this, the way people are sort of trying to accomplish this sending of quantum states over long distances is using light pulses, which are sometimes called photons. And you'll probably hear me use that word. And I think you guys have maybe heard it before. So this is sort of the idea of the quantum internet, sending quantum states over long distances using light. So defect centers. So what is a defect center? So if you were to zoom in on a material like a diamond, for example, really, really close, you would see something like this structure over here, where there's a bunch of atoms in sort of this crystal. Here, these green atoms are carbon, but occasionally there will be a defect. So a mistake, sort of a wrong atom. So here, for example, there's this nitrogen atom, and then this V is a vacancy. It's just a missing atom. And it turns out that if you make this thing, you sort of replace one of these atoms in the crystal with something else, you can make a qubit. And the way of thinking about it is it's basically a lot like the trapped ion system that David just talked about. But instead of trapping it in this vacuum chamber using these, electric fields and things like that, it's basically trapped by the surrounding material. And so this is sort of a trapped ion that nature has just given to us. And the really cool thing about this area of research, this type of qubit, is there are lots of different sort of species, is the word people use, of defects inside of lots of different materials. So here on the left, these are all diamonds, but these are diamonds that have different kinds of defects in them, ranging from nitrogen, silicon, oxygen. And you can see that they all kind of change the properties of this diamond. And each one of these kind of acts as a qubit with its own pros and cons. So the most popular of these, and the one that I'll probably be talking about the most today, is something called the nitrogen vacancy defect in diamond. So that looks like this over here. There's the diamond crystal, and one of those atoms is replaced by nitrogen, and one of them is sort of just a missing atom. So how do we actually make these things? So we actually grow diamonds. So this is something called a chemical vapor deposition tool. And it's basically a giant microwave. So we take some gas in and we send in microwaves into it, and it heats up the methane gas that we put in and literally grows the diamond. And once we have this diamond, what we do is we want to then implant those defect centers. So it's all carbon. We want to add in the nitrogen. So we'll take some source of nitrogen and heat it up and sort of send it at high speeds, impacting into this diamond, and it sort of buries itself in there to form that defect. And then the last thing we do is that process damages the diamond a lot. So we'll actually heat it up in a process known as annealing. So this is something that we built in our lab. This is basically a vacuum chamber plus some heating elements that get our diamond up to 1500 degrees Celsius. So very, very, very hot. And that process sort of heals the diamond. And after we do all this, if we look at the diamond under a microscope, we see something like this. So you see each of these little small dots is one of those nitrogen atoms, one of those defect centers that we formed that now glows brightly. And I'll talk about what that glow is in a little bit. So how do we actually use them as qubits? So we have this atom, it's inside of this crystal structure, and the electron that's associated with that atom, the atom has electrons spinning around it, the spin of the electrons around it forms our qubit. And so we say if it's spin down, we call that qubit state 0. And if it's spin up, we call that qubit state 1. And okay, the things we need to be able to do for a qubit, we need to be able to read it out, of course. So it turns out that we can read the state of the qubit using lasers. So if we shine a laser onto the qubit and it's in this 0 state, what will happen is it'll absorb that light and then emit out light. It'll emit out photons, and it'll be very, very bright. So that's what we saw on that last slide. All those little dots were qubits in state 0. However, if it's in qubit state 1 and we shine that light onto it, it turns out that it can't absorb the laser in this state. And so it's actually dark. So that's how we read it out. Basically, shine a laser on it, bright 0, dark 1. Okay, what else do we need to do? We need to be able to control it. So it turns out that you can control the qubit by sending in microwaves. And these are like the same kinds of microwaves that are in the microwave in your house. We just sort of direct them at the diamond. And it turns out that we can sort of cause the qubit to go from 0 to 1 and back and forth. And we can do this with very high fidelity and very high speed. And so actually combining these two things, what happens if we apply microwaves for some amount of time and then read out the state of the qubit? What we see is that as the qubit undergoes a longer microwave sort of pulse duration, so we apply microwaves for longer, we see the qubit get dimmer, then brighter, then dimmer, then brighter. And that's exactly us moving from the 0 state, the bright state, to the dark state, and back and forth and back and forth. And so this is how we can control the state of the qubit and read it out. So kind of a bonus, and something I really want to emphasize with these solid state qubits. What happens if we apply microwaves and prepare a superposition state? So you guys have seen this state before, and then apply this laser pulse. Well, so the 0 term wants to be bright, it wants to emit a photon. The 1 state wants to be dark, it wants to not emit a photon. And so what actually happens is we get a superposition of being bright and being dark. And another way of looking at this is that this process, creating superposition, then applying light, creates entanglement between the spin of the electron and the number of photons, or the amount of light that we've emitted. And this is a really, really special thing, because we can take that light and now send it long distances for quantum networking. I'll talk a little bit how we can do that in a couple slides. So how do we actually operate them? What does this look like in the lab? So we need to make these things colder than the trapped ions that David talked about, but not quite as cold as the superconducting qubits that Amir talked about. So we use this device over here on the left. This is called a cryostat, and it uses liquid helium to cool everything down to around 4 Kelvin. It's the temperature of liquid helium. And so it's pretty cold. Colder than anything you'll come across, in day-to-day life, but not quite as cold as the superconducting qubits. And if you were to open this thing up, this is something in our lab, you would see a chip that looked a little bit like this. So this is some circuitry for sending electrical signals, those microwaves, on and off the chip. And then if you were to zoom in even farther, you would see something that looked like this. So I added that spin. That's not what it looks like. But this is sort of a kind of a lens, actually, sort of a little bubble that we've carved out over the defect center that sits at the center. And we can send light in and out of it via these mirrors over here on the left. And we also have these sort of gold lines that we've put onto it, literally made of gold, that we stick onto the diamond to let us send microwaves in and out. And so then the last pieces that we need for controlling this qubit, we need some lasers. Just a picture of a very, very strong laser we have in the lab, and then those microwaves. And so this is a big box that I think was probably made in the 80s. It's very old, but just can produce microwaves and send them down to a controller qubit. So, okay, so this is how we control a single qubit. How do we actually connect the qubits up and entangle them? That's the key, right? We want to entangle the qubits for these 2 qubit gates. So it turns out that for defect centers, there are 2 options. So one option, if the qubits are very, very close to each other, something like 10 nanometers, so very, very close, it turns out that we can use a property of the spin to do a gate. So if you have an electron spin, in the same way that if you have like kind of a bar magnet that you can maybe buy from the store or something, it makes a magnetic field. And if you've ever done the thing where you have 2 magnets and you bring them close together, you can tell that there's some sort of interaction between the 2 because the magnetic field of one affects the magnetic field of the other. And so if you have 2 qubits that are very, very close together, their magnetic fields let them talk to each other. And specifically, there's 2 possible configurations. They can be in opposite directions. So one of them is up, one of them is down, one of them is 0, one of them is 1. And this is sort of a lower energy configuration, which again, if you've played around with magnets, you can probably feel this. Or they can be in the same direction. This is higher energy. And so what happens is if you have 2 qubits that are pointing the same direction, the Hamiltonian, the sort of interaction energy of these 2 qubits will cause a CZ gate to happen. This is basically, and I think you guys have talked about this. If not, we can talk about it later. But basically, the higher energy state causes one of the qubits to pick up phase and do this controlled Z gate, and this is a 2 qubit gate. So the advantage of this is that it's very, very fast, takes about a microsecond, and it's pretty high fidelity, over 99%. The con of this is that it is always on. These 2 qubits are inside of the solid crystal. They are 10 nanometers apart and they're not going anywhere. So you really can't turn this thing off. So you have to be very careful when you design your quantum circuit to make sure that you're keeping track of that. However, we have another option available to us. So for qubits that are far away, we can actually use a sort of a light mediated gate. So using those photons that are emitted. So the way we do this is as follows. So let's say we have 2 qubits and we prepare them in that way that I spoke about on the earlier slide. So we make this superposition, we shoot them with a laser, and so we make them entangled with the spin and the amount of light that's emitted. So we do this with 2 qubits, and then we take their emissions and overlap them on this special mirror. This is a mirror that is half reflective, half transmitted. What will happen is those photons will come from each defect center and sort of half of them will go one side, half of them will go the other way. And then if we take detectors, these black things are photon detectors. And if we measure a click, which says, okay, I saw some light, we know that one of the atoms emitted. But because of this special mirror that is 50% reflective, 50% transmissive, we actually can't tell which defect center emitted. So what happens is if we get one click, we actually move from having these 2 separate states to having this state where we know one of them was in the 0 state, right? Because the 0 state is the one that emits light, but we can't tell which one was which. So we have entangled the 2 qubits. And the really, really cool thing about this is that we can have these qubits be kilometers apart. They can be on separate sides of the universe, and we can send these 2 photons, and if we get a click, we will entangle these 2 qubits. So that's really, really special. We don't need them to be on the same chip. They can be anywhere. Now, the cons of this are that it's very, very slow. So I put 100 milliseconds, 0.1 seconds. It actually can be much longer than that, depending on how far apart they are. And the other thing is that it's probabilistic. It doesn't work every time. You can imagine maybe they both emit a photon, and then we don't get any clicks. Okay, then we have to start over. We have to prepare the state again and try again. So there are these 2 options available to us. We can connect qubits that are close, and we can connect qubits that are far, depending on what we're trying to do. So a really, really cool thing about these particular types of qubits is that they are already in a material. We don't need to do anything fancy to make them on chip. They're already on a chip. But we can actually do some additional sort of fun things using something called fabrication, which is basically just taking a material and sort of carving things out of it, doing sort of drawing patterns and things like that to make it into a more interesting circuit. And specifically, we can sort of carve wires out actually for making integrated circuits. So we use this tool, which is a reactive ion etch is what this thing's called. And basically it's a giant microwave that we put oxygen gas in, it heats it up, and then that oxygen forms a plasma that will eat away at the diamond and actually carve out, in this case, a wire. And so now that we have this little wire, what we can do is we can take it off of the diamond and put it onto something else. So this is something we made in our lab. So this blue here these are diamond wires that we've made. And at the center of each of these is one of these defect center qubits. And we put it onto some other chip that has some other wires on it. And so you can see what we can do is we can make some sort of complicated circuitry for taking light out of these qubits and guiding them around. And so there are two things about this. One is that we can very easily put many qubits on a chip. As you can see, this is an array of 8. We can just do that a bunch of times. And the light that's emitted by these qubits, we can now sort of collect it and route it around the chip, just like if we were making an electrical circuit. But instead of routing around voltages and currents like you would in a normal integrated circuit, we're taking light from these qubits that, again, is entangled with those qubits and moving it around on the chip. And I wanted to kind of dig in on this point because it's something that sort of separates these qubits that are in the material from other types of qubits. So you can imagine if you're trying to make quantum internet and you have an ion that's in a vacuum chamber, like the ones that David talked about. So you could do that same sort of thing, actually, it turns out, with an ion where they emit light that is entangled with their qubit state. However, the light from that is going to just sort of emit in all different directions. And so you can imagine if I want to take that light and I want to put it in like an Ethernet cable or fiber optic cable and send it somewhere, I'm not going to be able to collect very much of it. There's really only a small percentage of it because most of it's just sort of going in all sorts of directions. On the contrast, for these systems where we're in this material, what happens is if I carve out this wire, the light actually gets trapped inside of it. It can't leave out the sides, which means that when we go to collect it, we can collect a lot more of it. In this case, without doing any really hard work, we can get 50% of the light, which means that our quantum internet is going to be a lot more efficient if we have these materials where we can collect the light more efficiently. So kind of to summarize the pros and cons for this thing, they're very, very easily integrated onto a chip, as we saw. They can have pretty long coherence times, anywhere from 1 millisecond to some of the species of qubits can have minutes long coherence times. And the real cool thing is that we can use this sort of spin light, the spin photon entanglement to do gates between qubits that are very, very far apart. Cons, on the flip side, we do have to cool these things down to something like millikelvin or Kelvin temperatures. And it is actually quite challenging to connect lots of qubits. So, this long distance gate is useful, but it's actually hard to do that between lots and lots of qubits. And the last thing that is a problem that I have to deal with is that sometimes the materials are a little inconsistent. So sometimes we grow the diamond and it's really rough, or it has other defects that we didn't want in there. And that's sort of a challenge that people who study material science, which is a huge field that's also very important, they solve those types of problems. There have been a number of landmarks using this qubit. So a couple of them here. One that was very famous, got a lot of press. There was an article in the New York Times even about it, was the first demonstration of entangling 2 qubits at long distances. And this was over 1 kilometer. And they actually used it to basically show something called a Bell's inequality violation. Basically, they proved that quantum mechanics is true. They proved that quantum mechanics is the correct theory, which was a big deal. And since then, there have been actually lots of useful things as well. So this came out last year where people actually did this sort of quantum cryptography, this quantum key distribution that I mentioned, and actually used it to beat what you could do without using quantum capabilities. So that's pretty cool. Last year as well, this came out actually from my own research group. There's me buried in the author list. We made a chip where we integrated 128 of these individual atoms onto one single chip. So showing that there's some sort of, this scales well, we can put lots of them on one chip without too much difficulty. And then the last thing I'll point to, this actually just came out, I think like last week or so. This was published in Science, where they actually show demonstration of entanglement between 3 different nodes. So 3 qubits that are all separated by distances and showing that you can entangle all 3 of them. So the work that people are still trying to do in this area, I mentioned that, this NV center is really just one of many, many kinds of species of defect centers. So people are always hunting for new kinds of defects and new kinds of materials. So this is something that I've been working on recently. We tried taking not nitrogen, but lead and implanting that in the diamond, seeing, okay, what does that look like? Is that better or worse? What can we do with it? And similarly, we're also trying to just improve the materials that we implanted in. So this was a diamond that some of our collaborators grew that is very ugly. Turns out it's very hard to, but something that we're working to. We're also fabrication, so that carving out of wires for guiding light around. We want to do better at that. We want to see, okay, can we make more interesting ways of guiding light around that will give us more tools at our disposal. We do have a lot of work to do relative to these other systems of faster and higher fidelity 2-qubit gates. That's definitely a weakness of this system. But finally, we want to just put more qubits on one chip. So this is something that we made in our lab where each of these little grids is one of those arrays of 8 wires. And so this chip has thousands of qubits on one chip. And so we're constantly trying to improve the number that we have. And I have some additional reading here. I guess people can like screenshot this or we can share this out later or something if people want to read. And most of these articles are sort of ones that are written for your kind of audience. So like some quantum background, except for this one's a bit more technical, but these other ones are I think good ones that people can read if they're interested in this area. Cool, thanks.
Thank you so much, Eric. And I guess that brings us to our last speaker, Stefan, who will be talking about photonic quantum computing.
Yep. Give me a second to share screen and I'll start.
And as always, everyone, we will post the slides on Canvas, so you'll have access to Eric's slides with the links and everything you've seen today.
Okay. So, hey everyone. I'll be discussing the photonic side of much of the hardware we've seen today. First, a bit about me. My name is Stefan. I grew up in Bulgaria, spent some time studying in France and the US, and now I'm working at the MIT in the same group as Eric. As many of the discussions of hardware today showed, we use light for a lot of the interaction with the qubits we've been discussing. And I'll focus a little bit more on those, on that light interaction, how it's used, and how we can maybe even skip some of the implementations mentioned today and just jump directly to use just light as the medium carrying the quantum information and working with the quantum information. So in very briefly, why we care about light as a carrier of quantum information is that it's resilient to many of the types of noise that have been discussed today. But on the other hand, light itself is very difficult to make interact in ways that enable us to make 2-qubit gates. There are also many different ways to use light as a carrier of quantum information. We can say that the presence of light is the state 1, the absence of light is state 0. We can say that the polarization of light, whether it's vertically or horizontally polarized, is related to the 0 or 1 state of a qubit. We can even talk about the time when light arrives, whether it arrives now or a nanosecond later. That can be the way we encode quantum information in light. I won't be discussing any of those topics because that would make this talk into at least an hour-long talk. Instead, we'll focus on the features of light that are shared among all the ways in which it can be used as a quantum carrier of information. With that out of the way, I want to focus a little bit on the good things about using light as this carrier of information. And this was seen a lot during the discussion of quantum networking in the previous talk by Eric. But optical hardware doesn't need to be cooled unlike any other type of hardware. So if we want to create a network where we transmit a qubit from node 1 to node 2, and we don't want this entire network, this kilometer-long cable, to be cooled itself in a gigantic cryostat, we will need to use fiber optics that carries the light. And that's something that cannot be done with microwave qubits. That's something that truly only light has this room temperature resiliency. And let's spend a couple of minutes to try to understand why. So in multiple of the previous discussions, especially when it was talked about T1 times and the lifetime of the qubit, there were drawings of this type where we had a two-level system, and we're discussing that such a two-level system used as a qubit will have finite memory time, finite lifetime, because the qubit will be decaying into its ground state, and a photon of light will be released and sent in the environment. And also, when we're talking about microwave qubits, we were discussing how a photon from the environment can hit that two-level system and excite it, and again destroy the information that was carried in it, because this photon it's not something we controlled. It was just from the thermal background, like any hot object sending infrared radiation and just exciting your qubit and destroying the information you wanted to store in it. And that's why with the microwave, the superconducting qubits, we had to cool them to millikelvin temperatures. Let's see how this compares to other types of implementations. Here I have a quick graph that shows a bunch of different curves for different temperatures. And each of those curves represents the type of radiation coming out from an object at the given temperature. For instance, an object that's at the temperature of the sun's surface will be radiating light in the visible spectrum, some UV light, and some infrared light. But an object at room temperature will not radiate anything that's at the wavelength of optical light. An object at room temperature is not a source of visible light. And if you look at really, really low temperatures, for instance, 100 Kelvin, even at that temperature, an object like that will be radiating electromagnetic radiation on a scale that's still capable of exciting a microwave superconducting qubit. That's why we have to go really far right on this graph with very, very cold temperatures, so that the thermal radiation from our surroundings doesn't excite our microwave or superconducting qubit. On the other hand, to destroy a qubit that's in the optical regime, we need a really hot object. Room temperature is much too low to generate spurious visible light radiation. So if our qubit is actually a visible light photon, or some arbitrary amount of visible light, that qubit will not be disturbed by the thermal radiation of its surrounding. So as long as we have the fiber optics carrying that qubit, optically isolated from its surrounding, the thermal radiation generated by its surrounding itself will not destroy the qubit. And that's one of the main reasons we care about photonic qubits. But now let's spend some time on discussing the issues with photonic qubits, because if they're so great, why is not everyone just using them? And that would come to the idea of 2-qubit gates. And again, the exact type of 2-qubit gate depends on how exactly we're encoding the quantum information in the photon. And we won't discuss all the different options to do that. But in either of those, in any of those cases, we need different packets of light, different waves of light, or different photons to interact with each other if we are to perform a gate between them, whatever that 2-qubit gate is. And in this picture, you can see a very important experiment that tells us that this would be difficult. If we have two flashlights shining towards each other, the rays of light they generate just pass through each other. They don't interact. They don't reflect each other. We don't turn a bunch of photons from one of the beams of light into photons from the other beam of light. And that's the gist of the issue we have here. Light, electromagnetic waves are inherently linear, if you want to Google the mathematical term describing this behavior. Another way to phrase this, if just in terms of a Googleable term you can look up, is that electromagnetic waves obey classical superposition principle, that two different waves will not will just pass by each other without modifying each other after they've passed by. And now we need to find a way to work around this limitation. Well, there are a family of very special materials with names like lithium niobate, materials in which when you send a packet of light of a given color, that light is modified and a different color can come out. And those materials generally, the effect in those materials is fairly weak. It's really difficult to find the material that has those properties. And even if we find the material with such properties, it's really difficult to fabricate out of this material a device in which those properties are sufficiently magnified. But pictorially, what happens is that in a material of this type, you send some light. For instance, in this picture is some infrared light sent in the material. That light will force the atoms of this material to collectively move. But in this special type of materials, the interaction between these atoms is such that it can create a new type of light, not the type of light that came in. Those materials are called nonlinear. And again, this comes down to the theory of electromagnetism that lets us describe those. And I'll be happy to talk a little bit more about it later. But the detailed physics of how this happens is not necessary to understand the phenomenon that we'll be exploiting. The phenomenon that we'll be exploiting is that in a material like that, two different light waves can interact with each other in ways that they do it in vacuum. And as I mentioned, those materials are actually really difficult to work with for the moment. So as a workaround, we have been trying to use just special types of atoms, NV centers, ions, as something that mediates the interaction between light. And those were the last two talks. They describe very much how light can interact with this very special atom or defect center. But the issue is that if we have to use those atoms or defect centers, then we go back to the fact that we need very low temperatures for those devices to work, because the atoms or defect centers will not be reliable at high temperature. So while this is a great workaround, it also loses one of the best things about using purely photonics for interaction. And just briefly in the next minute or two, I would like to go through a couple of examples of how we actually try to capture, store, and manipulate light. Because in many of the pictures you've seen up to now in the talks, you saw big optical tables with a lot of mirrors and fibers and so on. But if for every single photonic qubit that we want to use, we have to place a microscopic mirror, well, that's a ton of manual work, and that this definitely will not scale. So we need to discuss how we are going to put light on a chip in a way in which we can have millions, if not billions, of photonic qubits in a single location. And another problem we have here is that light, unlike all the other types of qubits we discussed up to now, is something that just us. We need it if we're going to working tool for communication, but as a tool for computation. So let's see how we can do that. And an inspiration for actually, let me jump to, a chip that can store light in that fashion would look something like this here. This millimeter scale picture of a chip, and on that chip we can use the same techniques used to create modern semiconductors in order to deposit something that looks like very much a piece of fiber optics, but deposited directly on the chip. We have the substrate on which we'll be building this set of optical wires, and using the same techniques we will be using to place an electrical wire, we place an optical wire. It's called a waveguide. And here pictorially on top of the waveguide is shown in this fake colors just added on top, where the light actually will be passing through. So the light enters this waveguide and propagates through the waveguide, where most of the content of the light, most of the intensity of the light is in the center of this waveguide. And here are a couple of pictures of elements that we can build in this type of circuit that will be used to store the light. And shortly, I'll describe how that works. But basically, light passes by in this waveguide, and part of that light will be transferred to this element that stores the light. And let's see how those work. The inspiration for this type of elements actually comes from something called whispering galleries. One of the first accidentally discovered whispering gallery being in a cathedral in London. And how do those work? The whispering galleries are the same type of storage device, device in quotes, but for sound. If you have under the rotunda of the cathedral, you can have this circular structure in which a talker says something and the sound reflects on the curved walls of the cathedral, and it efficiently reaches the listener, and it just continues going round and round. And a listener on the other side of the cathedral can hear even a whisper from the talker, exactly because the sound is directed in this fashion. And we can do the same optically. We just need a material in which, when the light is trapped, it just continues going round and round and round. And to do that, we use the fact that light can reflect in a phenomenon called total internal reflection when facing a sufficiently large difference of refractive indices between two media. Here, a plexiglass tube and air, and we can see that the laser that enters the tube, you see that it just reflects, and it reflects again, and it never exits the tube. So we just shape this in a circle, and this would be our storage for light. What does this look like in practice? Where this less than a millimeter scale piece of glass, in which we can see in this picture actually the rays of light, how they slightly refract, and we see how some leakage of the light, but you can see how the light just goes round and round and round in this very small piece of glass. And on chip, those devices look like, well, simple circular waveguides or these mushroom-like structures. And that's how, if we can make those devices out of the special materials in which light can interact with other light, we can construct a purely photonic room temperature computer. But as I mentioned, that's still a difficult part, so ensuring that the interaction rates between light is strong enough. So with this, I just want to close up with the pros and cons. Obviously, comes on a chip, and there are a lot of caveats about this comes on a chip statement, and probably transmons and photonic circuits, it's truly fulfilled only in those cases. There are many caveats for many of the other devices discussed up to now. It's compatible with fabrication infrastructure. If it works, it would be extremely fast. And again, if it works, it would be at room temperature, like all of the other devices discussed up to now. And even if we cannot use this for computation, because it's efficient at room temperature, as long as we just want to communicate but not perform 2-qubit gates, we probably will have some other type of device like the ion traps or transmons or NV centers generate the qubits of light and be sent over the network. So whatever we end up with, the networking will definitely be photonic, unless you want to have cables that have to be cooled to millikelvin temperatures between all your nodes. On the other hand, those devices simply do not work today because we have such stringent requirements on those interaction rates. There are many interesting workarounds, but those would take too much time to discuss right now. And with that, I guess I would like to close.
Thank you so much, Stefan. So that concludes the talks that we had planned for today. And now we want to move to a Q&A session. I just want to emphasize one thing. So, you might have heard from a lot of panelists who are either affiliated with MIT or in the different ways or not have gone to MIT. But quantum computing and quantum information goes well beyond MIT. In fact, there are amazing places in Canada, for example, like the Institute for Quantum Computing or Calgary or many, many universities around the US and even in Asia who are very active in the field of quantum computing and are producing amazing research every year. So I just want to emphasize that.
As a European, I feel offended now. There are also really amazing places in all over Europe and many other places on Earth.
And a lot of the diamond results that I pointed to actually happened in the Netherlands. There's some of the best work in the world happening there.
Yeah, so it's truly a global field, and it's the global community is really pushing to advance the technology. So the panel is going to be moderated by Akshay. So Akshay, if you want to get us started with your questions.
Yeah, I want to maybe start with a few common questions that came up in the Q&A. I also want to thank all the panelists for answering some of those questions as they were coming up. But as we think about the different technologies that are currently being developed, do you think that maybe the type of technology that gets adopted will depend on the application? Or do you think that there's going to ultimately be one technology that everyone's going to be using?
Who's first?
I'll suggest that I think probably both, or probably some hybrid of things would be my guess. I don't know what you guys think, but it seems that different qubits are good at different things. And so, it may be the case that one qubit wins out at one task or another, but it would be surprising to me if there was one qubit that was really just truly the best at every single thing across the board.
Yeah, I agree with Eric. Okay, this is the Zoom problem that we have here. And I just want to
then, Stefan.
Okay, sounds good. And I just want to add on to Eric's point that, for example, superconducting qubits are really good at, as of now are really good at, or the best, one of the better technologies we have for quantum computing. When it comes to long-range communication, what we see is that the microwave photons that they would use for communication are actually very lossy. So as of now, it seems like superconducting qubits need improvement / are not potentially the best technology for long-range communication, whereas NV centers in diamond are.
Oh, I'll push even further. It's fundamentally impossible to use transmons for long-range communication unless you put your whole fridge in a shipping container.
Yeah, I will also argue that the photonic qubits is probably the best for telecommunications. For memory and storage, you have to have long coherence times. And as it is now, I mean just as it is now, because this I'm speculating from the future. It could be like tomorrow someone comes out with an excellent, solid state qubit or anything like that. As it is, ions in that sense is a good candidate because of the long coherence times. But yeah, I guess that as in any speculation, we all could be wrong. But what is interesting is that still there is people talking about, pushing and investing and doing all sort of advancements to the fields. So that would be my
And
take.
for what it's worth, it's not like classical devices have stuck to only one technology. In your own smartphones, there's actually microscopic acoustic devices that interact with electromagnetic devices, optics that has to then interact with electronics. It's fairly standard for our technological reality to be very mixed.
Yeah, but I think that differently that for like classical computers, the transistor was made of, I think that the first materials are not used nowadays. Now, it used to be a gallium and arsenide, and now it's silicon. So there are different materials with different properties, and it depends how easy it is to handle them. So I would argue it's similar, but in the classical world, choosing is easier in that sense.
Cool. Okay, then I think some people had confusions about how exactly gates are applied in different technologies. So I was wondering if each of you could summarize really quickly how are gates like applied in the technologies that you work on.
Yeah, so I could take a stab at it maybe, and then we can go in the presentation order. So for superconducting qubits, most gates are applied using microwave. So you can send microwave pulses down to our fridge, to our chip, and that creates a transition between 0 and 1. Now, of course, there are a different set of gates in superconducting qubits that you can create using the intrinsic interactions that are available in your system just by the virtue of your qubit talking or being connected to other qubits. And that's another set of gates. But the most common one right now that, for example, IBM's pursuing is all microwave based.
Just go in presentation
David,
order, David, I guess.
Yeah.
Sure, I can follow. So I think some people ask that for ions, what the best gate that we implement, and the one I explained, is called the phase gate. And that's not a CNOT gate, but you can think of a phase gate as some sort of fundamental unit for logic dividing of a more complicated gate. For instance, if you get like a combination of single qubit gates and a phase gate, you can combine these gates in such a way that the outcome is going to be a CNOT gate or a Toffoli gate or something way more complicated. But what we care about in the development phase is that you get the parts first, and then when you combine them, you get the outcome. So I would argue that many of us explain how to entangle, but everything starts with entanglement because it's quantum, and with entanglement or superposition. So in that sense, in ions, we get the phase gates and we get the single qubit gates, and we combine them to get the CNOTs, Toffoli, and the Shor algorithm and all of that. And demonstrations from all these platforms have been shown in the past, but that's usually how it starts.
Yeah, and then for solid state qubits, usually there are two types of things that we'll use. So when we want to control one qubit, we'll just apply microwaves that will kind of push it from 0 to 1 and vice versa. Well, then, okay, I guess three types. If we want to do the 2 qubit gate where they're very close to each other, the way we apply it is we just wait. So they just connect, and then we just let that happen. Then we actually have to wait twice as long. We wait for it once and then wait for it again to undo itself. And then for the gate where we do that entanglement between the spin and the photon, we do that by applying a laser. So we'll shine a laser for a certain amount of time, and then that excites it and causes it to basically emit an entangled photon. So microwaves or lasers or time.
And in photonics, usually what happens is that you use photonics just for the communication. So if you're performing gates, you'll be temporarily storing the photonics in NV centers or trapped ions. And there's a lot of work on trying to interface superconducting qubits with photonics, because superconducting qubits are the most promising in terms of computation today. And you need to transfer them to photonics to communicate between two computers. But then if we do ask about just using photonics for computation, not just for communication, Well, single qubit gates frequently are incredibly trivial. Like you use something called a wave plate or a polarizer, just change something about this, the orientation of that photon. And they're incredibly high fidelity. But 2-qubit gates, in normal materials, they simply don't exist. You need to have the photons interact. One way to do that, the one I discussed, the one if you really want to focus on pure photonics, is to use special materials in which light can be forced to interact with each other. And then there are some really interesting other modalities of quantum computer where you just build the computational fabric on completely different principles called cluster state quantum computation, blind quantum computation, and a bunch of other words that I'm just saying so that you can Google them. They have the same constraints, but they might be promising for other reasons.
Cool. And I'm seeing quite a few students in the chat were suggesting, why can't we make something that's like a mix of all of these technologies? And it seems like, Stefan, what you were suggesting is kind of that idea that maybe we can use superconducting qubits for the computation side of it, and we can use photons for the long distance of
That's a non-controversial opinion in our field.
Yeah, I would agree with that. It's just hard in practice to connect up these different qubits, you know. They all, so, you know, we mentioned that the superconducting qubits use microwaves and the defect centers use microwaves, but the way they use them is actually totally different. And, you know, the frequency of those microwaves is not usually the same. And so, you know, it's a matter of trying to not just develop the qubits themselves to be good, but also develop the technology that connects each of them together. So that's something that people are also working on. But right now, that's still sort of an active area of research.
Cool. And since we're coming up to the end, I want to end on an exciting note. So maybe I was wondering if each one of you could go around and tell us what you're most excited about in the future of quantum information science. What is, if you could pick one thing? So maybe we can start in the order of the presentations again.
Oh, I was hoping we wouldn't do that. This is a very hard problem, I feel like. So I think, in my opinion, the most exciting thing, at least in my area of research, you know, the next 10 years, let's say, would be to actually come up with a first useful demonstration of quantum advantage. So not sampling a random circuit, but rather doing something, you know, solving a chemistry problem, finding the most stable configuration of a molecule that classical computers just can't do. Or in other words, you know, or if it's, you know, much more efficient, much more faster than a classical computer, I'll also take that. Like, you know, if it takes my quantum computer maybe like, you know, 10 minutes to come up with the solution where it takes a classical computer a year worth of supercomputer time, I would also consider that a good useful application of quantum advantage. But I think that's what I'm looking towards, and it's not going to be in the near term. It's not going to be the next couple of years, but, you know, maybe 10 years we'll start seeing that.
Yeah, I actually have two things that make me feel excited that I think is going to happen in the near future. The first one is quantum error correction, like just to increase the amount of operations per unit of time. I think that, you know, getting a bunch of qubits is good, but if you have thousands of qubits and they are worthless, then I don't see any reason. You need to have algorithmic qubits to do anything useful with it. So as long as we keep those numbers to 2, 5 to 10, nothing really useful is coming out of that. So you really need to scale those numbers, but to do so, to truly do so, I believe we need error correction. So I think that is going to happen. If you feature anybody, I think that will agree that we are closer to that kind of near-end goal for now. And the second one that is probably not so evident for we practitioners of the quantum stuff is that the methods that we developed. So for example, Eric was talking about NV centers. I think that we will see an increase of people applying these methods to other fields. So I will give you an example. There were people measuring the electrical potentials of neurons using NV centers. And if then you apply then the quantum ways to read out this sort of phenomena, then that's just a whole different field that you open from there, right? And even like using quantum light, so for photonic chips, or quantum entanglement with photons to get microscopy techniques, for example. So I guess that's quantum computing probably is the hardest thing to do, but along the way, the methods, the theory, and all the things you will develop are going to be super important for also development in other fields. And to me, that's the second part of being excited, that it's just amazing that we have this beautiful theory that works so well, and the platforms that also work so well. So I think that it's also time to apply them to other like real life problems, not necessarily quantum computing only. So that would be my take.
Yeah, I want to piggyback on that point. I should just say that, like another example of that that's related to superconducting Q is that people are using these superconducting quantum circuits now to try to detect dark matter, which is not quantum computing. It's a totally different area of physics, but it's to address like same techniques to address questions about the universe.
Yeah, and actually, I guess the thing that I'm most excited for, again, is probably enough not a quantum computing thing, but sort of jumping off of what David said. So for the field of sort of quantum internet, quantum networking, quantum communication, whatever you want to call it, we're basically right now at the point where we can reliably send quantum states and create entanglement over reasonably large distances. And there are just lots of interesting things that you can do without even needing to have a quantum computer at the other end. So one of the things that I said is this quantum, like this secret key sharing. And there are, actually companies that are working on trying to do that without using memories. But if you actually have memories, you can do other sorts of things. So for example, relating to this sort of sensing area, I mentioned that, there are people who do sensing on like very, very small signals. So for example, like gravitational wave sensing. There are all these proposals out there that people have been writing about for decades of like, oh, if you had like a sensor here and it was entangled with a sensor over here, and they were on satellites on opposite sides of the earth, like you could get all these crazy higher sensitivities in your detection. And people wrote about that like decades ago, and now we finally have the ability to actually entangle things that are far apart. So people actually right now that these technologies have been demonstrated, there are a lot of space agencies that are actually working on getting these quantum memories in satellites so that you can actually make these sort of sensor networks. So like China put some satellites up. NASA has some programs in the US. I know there's some in Europe as well. The European Space Agency is working on. And so I think, sometime, it takes basically 5 years it's like 5 years out from those things actually being launched, and plus 3 years because the weather's bad or something. But I think sometime in the next 10 years, we're going to see entangled satellites doing lots of really cool experiments, measuring astronomical phenomena and stuff like that.
And I guess on my end, there's the idea that studying how mathematics, the laws of logic, can permit you to work with information just in the abstract are informative about what the laws of nature can be in principle. And studying quantum information, sure, it has all those absolutely earth-shattering applications, like being able to simulate new chemistry efficiently. That would revolutionize medicine. But there's also the idea that we are learning foundational facts about math and logic itself, and we can use those foundational facts to constrain the laws of nature. We get to learn out of purely abstract constructs like what quantum information is. We get to apply this to other fields of math and physics and actually understand more about the fabric of the universe. And this is completely unrelated to all the engineering applications. This is about trying to find the ultimate theory of everything and understanding how information in principle can be worked with, whether classically or quantumly, is a very important step for that.
Okay, since we're only 5 minutes over, I want to jump in with one final question and kind of give you guys a chance to talk about anything you haven't had a chance to mention yet. So what's one question you wish we would have asked that we haven't yet, or just really one final note that you want to leave students with, whether it be about your technology, quantum computing in general, or as they embark on their paths to learning quantum computing? And in any order, so we won't put Amir in the hot seat first.
Maybe one thing that oh, Stefan, go for it.
No, you opened your mouth first.
One thing that I was going to say, and I mentioned this briefly, is that quantum computing and quantum technology is really like a very interdisciplinary effort. And, kind of all the people that you're talking with right now are all kind of vaguely physicsy people. But there are people doing computer science work, people doing mathematical work, people doing materials work, chemists, people in all sorts of different areas that are working on different fields. And so if like quantum computing is something that you're excited about, there are tons of different ways to work on that as an area through different fields that maybe you're also passionate about. So I just kind of want to put that out there, that there are, this is a huge effort of people of different countries, different fields. And no matter what your skill sets are, interests, there are tons of ways to get involved.
And kind of related to what Eric mentioned, it took a couple of decades for classical computers to just become the tool you use in a lot of research. There is so much that you can do today in genetics because you have the cheap, powerful classical computers that simply wouldn't have been possible, even 20 years ago. And you don't need to be a computer engineer to use a computer efficiently in other field of study, whether it's engineering or biology or anything. And we're maybe this decade just about to start doing that with quantum computers. The same way 30 or 40 years ago, people finally started having a biology undergrad class that uses a computer to simulate something and do something that was impossible even 10 years before that. The same way, soon enough, we'll have just undergrad classes in, again, biology, where without knowing the mechanics of the quantum computer, you get to use those devices to do something that was impossible previously.
I can follow next, and I will ask you the kind of funny questions. Like I was a high schooler once, and I will ask myself, that is not being asked here, like what kind of jobs would you get if you get into quantum computing or anything related to quantum? And maybe that might sound too kind of like not on the topic, but it's also a concern. And I would argue that as a quantum physicist or any quantum information person, so for example, in ions, we use a lot of lasers. So I can also work as an optical engineer. As a theorist, you could work even in Wall Street because you already have the underlying math. Or you could do, type of like really, really deep mathematical aspects of any sort of science subject. And for that, there is a lot. So RF engineering for microwave people, or like photonic micro machining, or any sort of things. So as Eric and Stefan have all mentioned, it's multidisciplinary, but the beauty of that is that it gives you a bunch of skills that are also useful if you decide that you want to pursue a different path, or maybe you want to do something different. So I think that also like an aspect often overlooked, that if you're interested in science or you're interested in quantum, there is more that you will learn in the way, and the point here is to enjoy the path, and maybe the end result is a nice thing, but always enjoying your journey is a good thing for almost anything in life. So
like that would have been such a great note to end on, but now I guess I have to conclude something. So I think, like one question that was hinted to is, how would quantum computing relate? How would these quantum technologies relate to other technologies and other fields of, either STEM or just in general? Because it's a two-way street in a sense, right? Other fields can affect quantum computing, the same way they can use, for example, machine learning to better operate your quantum systems, or material science to engineer better quantum chips, but also the effect goes the other way. Like you can use a quantum computer to simulate material better, and then maybe you'll get a better understanding of how things work, and you can use that knowledge to engineer better processors. So I think one interesting question to think about is how do you see this dynamic playing out in, let's say, 5-10 years when when quantum computers have reached a certain maturity? And the question is, the answer is anyone's guess, but I think that'll be something that we'll see come up again in the future of quantum computing.
Well, thanks, Samir. Thanks, guys, for those beautiful wrap-up thoughts. I'm going to open up the chat because I want students to have a chance to really thank you all. Students really busy. Share part of your Sunday with us. Left, 2 labs left, and just appreciate everyone's time today. So we'll leave it open for just a second so you can see all the thanks coming in.
Thank you.
Have a great week, guys. See you in lab.
This was a lot of fun. Thank you, everyone, for coming.
All right, guys, thanks for your best wishes. I need to take care of some deadlines in my lab, so I'll see you. Take care.
See you guys.